This tutorial shows you how to work with Geographic Information Systems, GIS, spatial data in the form of vector data, such as shapefiles, using the open source and free software R. This tutorial covers importing, inspecting, transforming, and visualizing your spatial data. This tutorial assumes you are using Ubuntu Linux version 22.04 as your operating system, although it will work on Windows or Mac operating systems as well, as long as you have R and RStudio installed on your computer. This tutorial assumes the programs R and RStudio are installed. See the show notes below for instructions, or you can use my pre-configured virtual machine that already has all the programs you need installed. This tutorial assumes you have the R package SF installed. See the show notes below for instructions, or simply bypass all of the fuss and use my pre-configured virtual machine. I have a virtual machine pre-configured and pre-installed with various population genetics and landscape ecology software. You can run this virtual machine within your Windows or Mac computer. In fact, I am running Ubuntu Linux that you are seeing right now as a virtual machine within my Mac computer. See the show notes below for instructions to download and hook up this virtual machine to your Windows or Mac computer. Let's go ahead and get started. Open up a browser window, which I have pinned to my favorites on the left, or which you can find by searching below. Navigate to my website, joshbanta.com. Click on Tutorials. Use Control F to search for the tutorial called Projections, Transformations, and GPS Data Import in R. Click on it. Click on Files Needed for Tutorial. Click the Download button. When the download is complete, you may close the browser window. Open File Explorer, which I have pinned to my favorites on the left, or which you can find by searching below. Navigate to your Downloads folder and find the file projectionslablayers.zip. If you are on a Windows computer, right-click. If you are on a Mac computer, push down on the trackpad with 2 fingers and select Extract to. Navigate to your desktop and click on Select. You may now close the File Explorer window. Double-click the folder called Projections Lab Layers for R that is on your desktop. This folder contains the files that you will need for this tutorial. When using your own data, be sure that any files you will use are contained within this folder. Do not use any subfolders. Be sure that all of the scripts that I show you in this tutorial are in this folder, because you will need them when working with your own data. You may now close this folder. Next, open RStudio, which I have pinned to my favorites on the left, or which you can find by searching below. Select File from the drop-down menu, and then select Open File. Navigate to your desktop, and then click on the folder Projections Lab Layers for R. Click the file Projections Lab for R.R, and then select Open. First, make sure your working directory is set correctly. This is crucial for making sure R knows where to look for and save your files. Select Session from the drop-down menu, and then select Set Working Directory to Source File Location. Now load the SF package. Highlight line 6 and click on Run. In addition to the core SF functionality, we'll be sourcing several custom R scripts that contain useful functions for this tutorial. The scripts include functions for handling coordinate reference systems, geometry, projections, and more. You don't need to worry about them for now. Just know that they're here to streamline our workflow. Highlight lines 8 through 20 and click on Run. The first data set we're going to import is a shapefile containing information about Texas counties. You can import it with the stRead function and assign it to a variable called Texas counties. Highlight line 24 and click on Run. This function reads the shapefile and stores it as an SF object, which contains both geometry and attribute data. Now let's look at the geometry type of the Texas counties layer. Is it made up of points, lines, or polygons? To find out, we will use the getGeometry function. This will help us to understand what kind of spatial data we're working with. Highlight line 29 and click Run. The data type that we have is polygons. Next, let's take a closer look at the data. We'll use the viewSFDataFrame function to display the first few rows and columns of the dataset. This is especially useful when you're working with large datasets and want to understand their structure. Click on line 33, highlight it, and click on Run. This shows just the first 10 columns of data. Now let's look at all the columns of data. Highlight line 37 and click on Run. This shows just the first 5 rows of the data, the first 5 polygons in other words, but it shows all of the columns. Another way to look at all of the columns is to use the reportsfcolumns function. Highlight line 41 and click on Run. One column of particular interest is the geometry column. This column defines the spatial shapes of the counties. To understand its contents better, we'll use the reportsfcolumninfo function. For example, let's check out the aname attribute, which holds the names of all the counties in Texas. Highlight line 50 and click on Run. Now let's examine the Coordinate Reference System, or CRS, of the Texas counties dataset. The CRS specifies the spatial reference used, such as the ellipsoid, datum, and projection. We can easily retrieve this information with the process_sfObject function. This is useful for ensuring all your spatial data layers are using the same CRS, which is essential for accurate mapping and analysis. Highlight line 57 and click on Run. The ellipsoid is Geodetic Reference System 1980. The datum is North American Datum 1983. There is no projection listed because this data is stored on a model of a spherical Earth. The coordinate units for measuring distances are in degrees. The EPSG code gives all the information about the ellipsoid, datum, projection, and the units. This is a code that we can feed into R to tell R all of the information about our coordinate reference system. For more information, visit the links provided on lines 62 through 64. You can obtain more detailed information about this layer using the stCRS function. Highlight line 68 and click on Run. To visualize the data, we'll plot it using the Plot Layers with Interactive Zoom function. This will allow us to zoom in and explore the counties of Texas on an interactive map. Highlight line 72 and click on Run. Notice in the console window, you are being asked, do you want to zoom in? Select Y for yes and hit Enter. Now, look at the plot of the Texas counties. Click on 4 places forming a box. This will zoom the plot to the area defined by the box that you clicked. Notice that the console window is asking you if you want to zoom further. Click Y for yes and hit enter. Click another 4 points. This will zoom the plot even further. You are being asked now in the console window if you want to zoom further. Let's click on N for no. Now you are being asked in the console window if you want to zoom back out to the full spatial extent. Click Y for yes and click enter. Now you can see the full Texas counties map plotted on your screen again. You are being asked in the console window if you want to zoom in. Click N for no. Next, we'll import a second layer containing information about medical facilities in Texas. Similar to the first layer, we can use stread to import the data and store it in a variable called facilities. Highlight line 77 and click on Run.
This is a quick splice to ask you to consider subscribing to my channel by hitting the subscribe button. It does not cost anything. It is totally free. But if you like what I am doing and want to support my work, I encourage you to visit patreon.com/joshbanta and make a voluntary contribution. The link is in the show notes below. Your support helps me to deliver new content and keep this channel current and vibrant. Thank you.
Then try examining the geometry type, columns, and attributes of this layer. Just like we did with the Texas counties layer. You can use the same functions, but for the new facilities object. Follow the instructions on lines 79 through 100 and use the hints provided to help you get the information. If you are performing this tutorial for my class, I need to see you do lines 79 through 100 in your recording. I need to see you carry those out properly. Now plot the facilities layer. Use the instructions on line 102 and 103 and follow the hint to make this plot. If you are following this tutorial for my class, I must see you make the plot of the facilities layer and have it in your recording. Zoom in on the plot as well. When you are finished, zoom out of the plot and exit from the zooms, just like you did for the first plot. Now let's plot the medical facilities data on top of the Texas counties layer. Use the Plot Layers with Interactive Zoom function again. This time passing both layers in as a list. The layer that is listed first is the layer that will be plotted first. Highlight line 107 and click on Run. Type N for no in the console window to indicate that you do not want to zoom in. Where is the facilities layer? It is not being shown because the two layers have different coordinate reference systems. The two layers are not using the same model of the Earth and/or the same projection. Hence, they cannot be shown together. To see for yourself, highlight lines 114 through 116 and click on Run. Note all of the differences. To make sure the two layers can be overlaid correctly, we need to transform one of the layers so that both datasets use the same CRS. We can reproject one layer to match the CRS of the other. This is done with the stTransform function. For instance, we can reproject the facilities layer to match the CRS of the Texas counties layer. Highlight line 129 and click on Run. Or vice versa, we can transform the Texas counties layer to match the CRS of the facilities layer. Highlight line 133 and click on Run. Or we can reproject both layers to a common CRS using a specific EPSG code. Highlight lines 138 through 140 and click on Run. Once you've reprojected the layers, try plotting them again. Highlight line 147 and click on Run. This is where we transformed the facilities layer to have the same CRS as the Texas counties layer. Notice that the facilities layer is now plotting on top of the Texas counties layer, and we can see it. Let's zoom in for a closer look. In the console window, press Y and hit Enter to indicate that you want to zoom in. Click on 4 points on the map to zoom. When it asks if you want to zoom in further, click Y and hit Enter. Click on 4 more points to zoom in further. In the console window where it asks you if you want to zoom further, hit N for no and hit Enter. In the console window, when it asks you if you want to zoom back out to the full extent, click No and hit Enter. Now I want you to try plotting line 149. Then I want you to try plotting line 151. Then 153. Then 155. And then 157. I want you to try plotting these one at a time. So for instance, you will highlight line 49 and click on Run. Then when you are finished, you will highlight line 151 and click on Run. I want you to note when both sets of layers are plotted together and when they are not. Then I want you to try to figure out why you do not see the facilities layer plotted on top of the Texas counties layer for some of these plots. Look at the layers that are being plotted. Look at the names. Is it Texas counties versus facilities 2? Is it Texas counties 2 versus facilities 2, etc.? Try to figure out why you are not seeing the layers aligned in the situations where they are not both plotting. Let's now import additional layers, such as fire stations, land use data, fire hydrants, and transportation data using similar methods. The names of the layers to import are listed on lines 161 and 162. Follow the instructions on lines 161 through 173 and pay special attention to the hints pointing you to the line numbers that will help you follow these steps. Once all layers are correctly aligned, plot them together in one interactive map all together. I also want you to zoom in different areas of the map so that you can see the individual layers plotted on top of the Texas counties to make sure that they are all there. Follow the instructions on lines 175 to 180, taking advantage of the hint on line 178. For data sharing and future use, we want to save these processed layers out to a file that is accessible to other software. You can use the stwrite function to save your layers to files. See the example on line 187, which is made up, but it shows you the general structure. Within the parentheses on line 187, you first put the name of the layer that you want to save to a file. Next, in quotation marks, you put the file name that you want to save it to. I am using the GeoPackage format to save the file with the .gpkg file extension because it is more modern and reliable than the shapefile format that we had the files in when we imported them. Use the instructions that you find on lines 193 through 198 to guide you through this process. Save out every layer that you have transformed into a common projection out to a GeoPackage file. So for instance, if you transformed the facilities to a R object called facilities2 so that it matched the Texas counties layer, then you would write out to a file facilities2, and you could call that file facilities2.gpkg. Like that for all of your other layers. Only write out to files the layers that were transformed so that they all match up together to be able to be plotted together on the same map. Finally, we will wrap up by importing GPS points into R. GPS data is usually in the WGS 1984 coordinate system, which corresponds to the EPSG code 4326. Let's look at the sample GPS data we will be importing. Click on File Explorer, which I have pinned to my favorites on the left, or which you can find by searching below. Navigate to your desktop and double-click on Projections Lab Layers for R. Find the file lelabprj.csv. This is a comma-delimited text file. That is the format that you will need if you are using your own GPS data. For this tutorial, we'll just be using the tutorial data. There's nothing that you need to make. Let's take a look at it. Double-click on that file. Click on OK to open this file in LibreOffice. The format of this file is that the first column contains the longitude information, and the second column contains the latitude information. The first row contains the column headers lowercase x and lowercase y. You can have additional columns of information after that if you would like. If you were using your own data instead of the tutorial data, be sure that your file is formatted exactly the same as this one, with the first column containing the longitude data and the second column containing the latitude data, and the first column with the header lowercase x and the second column with the header lowercase y. You can have additional columns of information as needed after those first two columns. Each row represents a GPS data point, in this case of a fast food restaurant. And so I have an additional column of data with the name of the fast food restaurant at each of those GPS points. You may close LibreOffice. We will import the data using the import CSV as SF function. You would replace the name of this file with the name of your file. And for your own data, you would change the name of this R object to whatever you would like. But we will leave this all as is for now because we are using the tutorial data. Highlight line 220 and click on Run. I want you to use all of the information you've learned in this tutorial. Follow the instructions on lines 222 through 256, paying careful attention to the hints that give you lines to look at in the code. If you are recording this for my class, I need to see you do all of those steps that are listed in the instructions for you on lines 222 through 256. And that's a wrap. In this tutorial, you learned how to import, inspect, transform, and visualize spatial data in R using the SF package. With these tools, you can confidently work with geospatial data for your analyses and mapping projects. Stay tuned for other videos about how to perform GIS using R.